Good morning, Chem 20s. Our lesson today is on the strength of acids and bases. Acids and bases can be distinguished by a means of a variety of properties. Some properties of acids and bases are more useful than others to a chemist, especially those that can be used as diagnostic tests. You will see that our comparison chart here of properties of acids and bases are the same ones discussed in a previous video. I have placed stars next to those properties that we should not use as a test in the lab because they are unsafe laboratory practices when we're using real acids and real chemical bases. When we are trying to distinguish between the two, the ones that stand out as properties that would for sure tell us the difference between an acid and a base would be the pH, the litmus paper test, as well as how they react with an active metal. It is obvious if we compare different acids at the same initial concentrations. For instance, if we compare hydrochloric acid and acetic acid, both at 1 mole per liter, that they can have different degrees of acidic properties. For example, a very dilute solution of a strong acid could have a higher pH or lower hydronium ion concentration than a more concentrated solution of a weak acid. Therefore, it is critical that we control the concentration and temperature of the acid if we're trying to compare them. In terms of its empirical properties, an acid is described as a weak acid if its characteristic properties under the same conditions are less than those of a common strong acid. If we refer back to our acid table in our data booklet, we will remind ourselves that most acids are weak acids. We only have 6 strong acids that are above the hydronium ion line in our acid chart. All other acids fall underneath that line. So what I've done is I've created a little diagram here where we have our 6 strong acids, and they're actually in order from strongest to weakest. These are the ones that will follow the properties of a strong acid. I have then chosen 6 weak acids that you probably know already and that we've probably used. Okay, in the next few slides, what we're going to do is we're going to discuss the differences between strong acids and weak acids. So we can explain the difference between strong and weak acids using the modified Arrhenius theory and the extent of reaction with water. So if we take the example of a strong acid, and what we're going to do is we're going to choose HCl. We know hydrochloric acid is a strong acid because one, it's got high conductivity. Two, it's got a high rate of reaction when we drop active metal into it, like magnesium. We're going to see a lot of bubbles right away, a lot of hydrogen gas being produced. And we know it's got a relatively low pH, meaning a pH closer to 0. Well, let's take a look at our example, HCl, and we're going to add it to water. We know since HCl is an acid, it's going to donate a proton. And we know it's going to produce hydronium ion and chloride ion. Now, the one thing I want to concentrate on is this spot here where the arrow is. Up until this point, we've kind of treated every acid as an equal, and they're not equals. Strong acids actually respond very differently than a weak acid. So when you are a strong acid, you actually, when you write one of these ionization reactions, you actually get to use what you might refer to as a normal arrow, or what I would refer to as a quantitative arrow. This means that the majority of our reactants will proceed to products and break into ions in solution. That is why it has such a high conductivity, because there are a lot of ions, especially hydronium ions, floating around in solution. So for a strong acid, we're going to put a quantitative arrow from now on, and we're also going to say that the percent yield is greater than 99%, which means 99% or more of my reactants will go to products. This is significantly different than what we will see when we look at a weak acid. So down here, I'm going to put a little star next to this comment because I think it's truly important. The high concentration of hydronium ions in a strong acid gives the solution strong acidic properties and therefore a low pH. Because remember, the lower the pH, the lower our pH closer to 0, the more acidic our acid is going to be. Now, if we compare that with a weak acid, like acetic acid still conducts electricity, but it's going to conduct less. It still reacts with metals like magnesium to make hydrogen gas, but it's going to have a lower rate of reaction, meaning the bubbles are going to be slower. It's going to take the reaction longer to react with the same size and mass piece of magnesium. And when we test with a pH meter, our weak acids are going to have a relatively higher pH compared to that of a stronger acid. It's going to be a little bit closer to 7 than our stronger acids that were closer to 0. So if I take a look at acetic acid, which is a weak acid, it's below the hydronium ion on my acid chart, it's still going to donate a proton because it's still, if we think about this based on the definition, it's still going to make hydronium ions. And then, of course, when it donates the hydrogen, it's still going to make acetate ions. The difference is because this is not strong, because it's not highly soluble, right? Because we said when we looked at Biame, strong acids dissociate into ions. Now, will some of this break into ions? Of course it will. This is where it gets its acid properties from. And it's still going to turn on the light of the conductivity tester, but it's not going to be as bright. So we're not going to use a quantitative arrow for weak acids. Instead, we're going to use this special arrow, and we call this an equilibrium arrow. If we think of when we did equilibrium in the solution chapter, that means some of our reactants will want to go to products, and some of our products, once it gets here, though, they're going to react and they'll want to go back to reactants. Most of our substance will want to actually stay as reactants. Whereas in a strong acid, 99% or more wants to go to products. In a weak acid, less than 50% actually want to go to products and become ions. Therefore, and I'm going to put another star down here, the lower concentration of hydronium ions that are present in a weak acid gives the solution less acidic properties. Notice it's still acidic, it's just less acidic because it's going to have less hydronium ions. And therefore, it's going to have a higher pH value with regards to those of a strong acid. So we're noticing some big differences here between strong and weak acids. Mostly it's going to be this arrow and percentage that goes above it. Well, now that we've done acids, this is also true for bases. A base can be described as a strong base if it dissociates in an aqueous solution to increase the hydroxide ion concentration. Evidence suggests that all soluble ionic hydroxides are strong bases. We tend to like to say in Chem 30 that if it's got hydroxide in it, it's probably a strong base. So let's look at an example you already know quite well, sodium hydroxide. It's got hydroxide in its name, therefore we know it's a strong base, which means it's going to have a high conductivity in solution, and it's going to have a relatively high pH, closer to 14, 13 in that range. So I have my strong base sodium hydroxide. Because it already has hydroxide in it, we do not have to add water. Remember, it's just going to dissociate. So because it's strong, it gets the quantitative arrow into sodium ions and hydroxide ions. Because it's a strong base, we're also going to say it dissociates greater than 99% to products. Again, I'm going to put a star down here because I feel this part is important. The high concentration of hydroxide ions gives this solution strong base properties and a extremely high pH, right? Closer to 14. Now, if I compared that to a weak base, we would have to use the modified Arrhenius' theory and the extent to how our weak base reacts with water. Remember, weak bases do not contain hydroxide ions. They cannot dissociate to release them. Instead, they have to react or collide with water in order to produce a few number of hydroxide ions to get that base qualities. So something like ammonia gas, NH3, is a weak base. It's got low conductivity, still will conduct, it just will conduct less. And it's got a relatively low pH compared to a strong base. So the pH will be closer to 7 rather than closer to 14. So if I tell you that NH3 is a base, and that should be obvious by now, because if we think about it, ammonia is what is in most cleaning supplies, and we know that cleaning supplies are bases. So it's going to accept a proton from the water because, again, our goal is to produce hydroxide. So that means then water turns into hydroxide ion. And NH3, when it gains another H positive, is NH4 positive. Because this is not a strong base, I cannot attach a quantitative arrow. Because it's a weak base, I'm going to use an equilibrium arrow. And because it's weak, the majority of my reactants don't want to go to products. They don't want to dissociate. Therefore, weak bases have a percent yield less than 50%, meaning they favor staying as reactants instead of going to products. Now, some will go to products because the light on the conductivity testers is still going to light up, but not all like what would happen in a strong acid. Again, I'm going to put a little star here. The lower the concentration of hydroxide ions gives the solution less basic properties and therefore a lower pH closer to 7.